So this idea that we can add a weak acid and its conjugate base to a solution and thereby achieve control over the pH against the onslaught of an acid added or a base added is what leads us to the idea of buffer solutions. And the word buffer here means that that solution is capable of resisting pH changes from either an acid or a base. And the buffer solutions are very interesting because they use the weak aspect of the acid as a strength. And we saw that because we had both the conjugate base and the acid lined up on both sides of that beaker. And whether we added a base to it or an acid, we have a line of defense against either one of those. And the key point here is that the weakness of the acid means that the weak acid can coexist with its conjugate base. We've said this 2 or 3 times, but we want to emphasize it because it's the key aspect that the weak acid and the conjugate base, which is a strong base, don't attack each other, and that means they can coexist. And so for an acid dissociation, we can write that down as HA, our canonical acid, reacting with water that produces the conjugate base, and H3O plus, and that is an equilibrium for a weak acid. So we can write the acid equilibrium constant. That's simply equal to the conjugate base concentration times H3O plus divided by the concentration of the acid. And so this allows us immediately to calculate the pH. So if we take minus log of both sides, we have minus log to the base 10 of the acid dissociation constant. Then we have minus the log to the base 10 of the H3O plus concentration. And then finally we have minus log to the base 10 of the ratio of the conjugate base to the concentration of the weak acid. Okay, now we know that the minus log to the base 10 operator is just the P operator, so we can immediately go through and write this as pKa equals pH, and then we have minus log to the base 10 of the ratio of the anion to the acid. Well, the way we actually use this equation is that we solve for the pH in these mixtures, these buffered mixtures. So let's solve for pH. pH is now equal to pKa plus log to the base 10 of the concentration of the conjugate base divided by the acid concentration in both cases. Now that turns out to be an extremely important equation because it allows us to calculate the pH of a mixture given the pKa and the concentrations of the conjugate base and the acid. And it turns out that it also provides the ability to design buffering mixtures. That is, if we want a pH around some quantity like a pH of 3, then we would pick the appropriate pKa to nearly match that. And as we'll see by these quantitative examples we're about to look at, this is extremely helpful. So we have achieved a very versatile equation. And this equation is called the Henderson-Hasselbalch equation. The pH is equal to the pKa of that acid dissociation, in this case a weak acid, plus the log to the base 10 of the ratio of the concentration of the conjugate base divided by the concentration of the acid, the weak acid. And so when we want to design a particular buffering to handle a certain pH, we want to control that pH in the bloodstream of a human being to very close tolerances. And so we can do that simply by picking the proper acid-base combinations and then creating the solution by adding a salt from that conjugate base. So to first order, as long as the sufficient weak acid HA and conjugate base A minus is available, the ratio of these two, that is the conjugate base and the weak acid, won't change significantly. And the point there is that when we write out this equation, pH is equal to pKa plus log of the concentration of that conjugate base divided by the acid, as long as these quantities do not depart dramatically from 1, we can calculate immediately what the pH of that mixture is. Now, we could also do this by solving every single one of these equilibrium problems with a Rice table. There's no reason why that won't work. But the Henderson-Hasselbalch equation provides an extremely quick way of doing these calculations for buffered solutions. And of course, it's buffered because this quantity tends to be small. Now, the other thing that it does is it allows us to look at the pH change when we dilute a particular mixture. In other words, if I add water to my acid-base reaction, do I have to do the calculation all over again? And the answer is no, because I could add a huge amount of additional water. But if I do that, what I essentially have is that I take my conjugate base of my weak acid and I divide its concentration, that is moles per liter, by a factor of 10, but I also automatically do the same thing to the weak acid. And because when I cancel out the 10, this gives me exactly the same calculated ratio of the conjugate base to the acid, that means that I can do the pH calculation instantly for any dilution that I happen to add to that system. So it's a very quick solution, and it tells me exactly what's going to happen when I dilute that mixture.